Okay, now Shiraz will give us his third lecture on black holes in Yang-Mills theory.
Okay. So, in the first two lectures of this series, we've seen that we have perhaps almost unreasonably good qualitative agreement between the partition function of weakly coupled Yang-Mills theory and the partition function of strongly coupled n equals 4 Yang-Mills theory. Of course, the agreement is just qualitative, but before I continue, just let me for 2 minutes remind you of the main features of the agreement. Firstly, we have this nice diagram with 1 over del S by del E for the strongly coupled theory. And remember that if we translated this diagram to the partition function as a function of temperature, we found that for very low temperatures we had 1 saddle point. For intermediate temperatures we had 3 saddle points. And then at high enough temperatures, once again, we had a single saddle point. So as you raise the temperature, the number of saddle points in your partition function goes from 1 to 3 to 1. Okay? At some point there's a phase transition between this and this saddle. This saddle is always unstable. Now, we've understood how to compute the thermodynamics of weakly coupled Yang-Mills theory up to an undetermined sign for the n equals 4 theory for this constant that comes from the 3-loop calculation. And you remember that if the sign had turned out to be negative, that is the case that most closely gives us the simplest phase diagram, just the first order all the way, then we would have got this set of diagrams for the effective action as a function of ρ1. We'd have got at very low temperatures something that looks like this, and at higher temperatures something that looks like that, and then at still higher temperatures something that looks like that. Okay? So once again we see the transition between a single saddle point, okay, to 3 saddle points. This one, and this one, and then to 1 saddle point. Okay? So if we make the correspondence that these saddle points coincide with each other, we've already seen that the saddle point at the edge of this ρ1 space, well, that should be said a little more precisely, but anyway, should be thought of as the analog of the big black hole. This saddle here is clearly the confining vacuum. Okay, it's the analog of thermal ADS. Whereas this black hole may perhaps loosely be thought of, and this is a very loose identification. For instance, because SO6 symmetry breaking never happens in the weakly coupled theory, but does happen for small black holes in the strong coupled theory. But roughly speaking, this could be thought of as the loose analog of the saddle point corresponding to small black holes. Okay? So in this broad qualitative structure, we see rough agreement in the structure of the partition functions between weak and strong coupling, provided alpha is negative. Okay? And as David Mateos also emphasized in his last lecture, and would also have followed from the detailed formulas that we've been discussing if we process them enough. If you look at extreme limits, for instance, if you look at the limit t goes to infinity, by which I really mean t times r goes to infinity, because that's the only dimensionless number in what we've been talking about, you can actually quite simply compute the partition function from weakly coupled Yang-Mills theory, and that agrees in functional form with the answer for the partition function from the strongly coupled Yang-Mills theory up to a constant number of order 1. Okay, so everything seems pretty good qualitatively. Okay, great. So now you might wonder, you might think then that Yang-Mills theory at reasonably weak coupling, or very weak coupling, gives you a good handle on the partition function of the theory, or the density of states of the theory graded with respect to all charges. Okay. However, that's not quite true. Okay, suppose you compute a more fine partition function than just the partition function as a function of temperature. So suppose you computed something like the following object. Okay, so before I do this, I should give you a 2-minute introduction to the symmetries of Yang-Mills theory on S3, n equals 4 Yang-Mills theory on S3, or equivalently 2B string theory on ADS5 cross S5. So each of these theories enjoys invariance under a large supersymmetry algebra. Of relevance to my lectures, the only thing that will be relevant to my lectures, the part of that algebra that will be relevant to my lectures, is the bosonic part. So I remind you that the bosonic part of the symmetry algebra is SO6, which from the point of view of Yang-Mills theory is the R symmetry group, or from the point of view of the string theory is the symmetry of the S5, times SO4, 2, which is conformal symmetry or the isometry group of ADS5. Okay, now this SO6 has rank 3, so there are 3 charges that you can simultaneously diagonalize, simultaneously measure classically. Okay, let's call these 3, let's choose a basis for these 3 charges. Let's call them H1, H2, H3, where H1, H2, and H3 are simply the operations of rotations in the orthogonal 2 planes of the R6 in which you can embed the S5. Okay? Similarly, for SO4, 2, for SO4, 2, we could break this up into its maximal compact subgroup, which is SO4 times SO2. The eigenvalue under this SO2 is simply the energy, so that's a very familiar conserved charge. And then we've got 2 different charges, let's call them L1 and L2, corresponding to the rotations in orthogonal 2 planes of the R4 in which the S3 of ADS5 is embedded. Okay? So the net upshot of this is that on both sides we have 6 commuting conserved charges. Okay? And we can weight states in Yang-Mills theory, or in type 2b string theory in ADS5 cross S5, with respect to each of these conserved charges. Okay, so the most general partition function that one could compute in n equals 4 Yang-Mills theory would be z, which is trace of e to the power minus beta e, then plus nu I hi, and then plus omega a la. Okay, the most general partition function weighted with respect to each of the conserved charges. Okay, now if we try to undertake the following exercise, suppose we try to compute this partition function for simplicity setting the omegas to 0, but weighted with respect to chemical potentials, the chemical potentials with respect for the SO6 charges. Okay, we did this calculation in pre-Yang-Mills theory. It's an easy calculation to do. It mimics the calculations we've been doing over the last 2 lectures. I won't go through any of the details, but I just want to tell you that if you do this calculation in pre-Yang-Mills theory, and then you do the calculation in n equals 4 Yang-Mills using what you know about black holes in n equals 4 Yang-Mills theory, you get answers that are qualitatively different. Okay? The answer that you get, in particular, this qualitative difference shows up. In particular, this qualitative difference shows up when you try to make the shows up most clearly when you try to make the charges and energies of your states large in Yang-Mills theory. Okay, so let me give you the right answer firstly from black hole physics. The right answer at strong coupling from black hole physics. I'll indicate what happens when you do the calculation in weakly coupled Yang-Mills theory, and then I'll outline a strategy of making progress in understanding this more general partition function, where we back off a little from our main goal of trying to solve everything using pure Yang-Mills theory. We're using some effective Lagrangian, as I'll tell you. Okay, so suppose we didn't know anything else about the theory. We just relied on symmetries and general principles, and we tried to ask, what does log of z look like, where z is this quantity? Let me first work with omega equals 0. Well, what could we say? So let's use the kind of arguments we've used before in these lectures. Firstly, this quantity should be proportional at high enough charges, or high enough temperatures. Okay, and let's stick to that limit for now, to the limit of very high charge densities at high temperatures. This quantity should be proportional to the volume of the space from extensivity. Okay, now z itself is a dimensionless quantity, so log of z must also be proportional to t cube. Okay, just by dimensional analysis. See, because no other quantity here has dimensions. Okay, but then, in addition, it could depend on a completely arbitrary function of these dimensionless variables nu I. Okay, so just from general principles, we might, you would say that this function here must take the form v t cubed some arbitrary function of nu I. Okay, this was our analysis. This was our analysis when omegas were 0. Okay, about this, it's true. Okay, this general analysis is made based on general principles, but can be verified by comparing with the formulas of static black hole thermodynamics. Okay, you look at the static black holes, you compute the entropy using the Hawking-Bekenstein formula, you compute all other charges using standard gravitational formulas, and you can check that the thermodynamics of these black holes is well reproduced by such a formula for a particular choice of h nu I, which I'll describe to you in a moment. Okay, in these lectures, I will have nothing to say about how one can go ahead and compute h of nu I. Okay, this is a very interesting function. It has very interesting functional dependence on these nu i's. It's much less trivial than t cube, which follows from dimensional analysis. Okay, and if you could compute it somehow using some strong coupling Yang-Mills dynamics, that would be a huge, fantastic achievement. But I'm not going to. I cannot do it, and therefore I will not try to do it in these lectures. Okay. However, what we are going to try to do is the following. See, suppose now we were to generalize our ambit. Suppose we wanted to compute the log of the partition function not as a function only of nu i's, but also of omegas. Okay, so using the same dimensional analysis arguments, you would say, well, there is some v t cube, and let's call this h tilde of nu I and omega. And dimensional analysis doesn't tell you any more. Okay, the aim of this lecture will be to demonstrate to you that you can, using some very general principles of quantum field theory, in an appropriate limit, entirely determine the omega dependence of this function. Okay? So what we're going to do is to use some very general principles of quantum field theory to completely determine the omega dependence of this function, and then compare against black hole physics, and we'll find very good agreement. Okay? That's the goal of this lecture. Say nothing about nu I dependence, but determine omega dependence. Any questions or comments before we proceed, before I try to tell you how we can go about doing this? Okay, great. So how are we going to go about doing this? You see, we're going to be working with n equals 4 Yang-Mills, strongly coupled n equals 4 Yang-Mills, about which we know very, very little. Okay? So the only properties of this theory that we can use are properties that are universal and follow generally from the basic principles of quantum field theory. So what do we know about quantum field theories in general? Well, there's one fact that we know about all quantum field theories. Okay? And that is that at appropriately high energy densities, the dynamics of these quantum field theories is well described by an effective set of equations, namely the equations of fluid dynamics. Okay, so let me remind you what fluid dynamics is. You see, suppose you've got a system in which everything is locally in thermodynamic equilibrium, but the parameters of this equilibrium vary in space and time. Okay, this variation has to be appropriately slow. And we'll study what appropriately slow means in a little bit. Okay, but supposing this is true, then in order to specify the system, all you have to specify are the quantities that specify the equilibrium of the system. So for instance, the temperature and chemical potentials of the system at each point in space and time, plus you have to account for the fact that the stuff that's in local thermal equilibrium can all be moving with respect to your lab frame. Now this is not just a frame issue because different things move at different speeds. Okay? So in some appropriate limit, and we'll describe what that limit is in a moment, but in some appropriate limit, there should be an effective description of dynamics whose variables are t of x, nu x and t, space time, nu I of x and t, and u mu of x and t, where u mu is a 4 velocity. Of course, the 4 velocity is constrained such that u squared is equal to -1, so only 3 variables in that 4 velocity. A lot of what I'm doing, by the way, will very trivially extend to d dimensions. So at some point I'll forget that we're dealing with a four-dimensional field theory and work in d dimensions in generality. Okay, so this is the main physical input once again. It's as follows. If in some appropriate regime, which we'll characterize soon, okay, it should be possible to describe effective dynamics in terms of a space-dependent temperature, space-dependent chemical potentials, and space-dependent velocities of your stuff. Okay, great. So these are the variables of fluid mechanics, that we understand. Now, what are the equations of fluid dynamics? Well, the equations of fluid dynamics are just a tautology, well, not a tautology, but an automaticness. Okay, the equation of fluid dynamics, simply the equation of conservation of these quantities. So the equation of conservation of the stress tensor and conservation of other conserved charges. These are, of course, very general equations and are always true. All the dynamical information in fluid dynamics, the thing that distinguishes one fluid from another, comes in specifying what the stress tensor and what the charge current is as a function of the variables of fluid mechanics. How do you do that specification? Well, of course, if you were infinitely clever, you could solve infinitely strongly coupled dynamics. But let's suppose you're not. Okay? Then what do you do? Well, what you do is to use the fact that the whole idea of fluid dynamics rests on slow variations. Okay? Because it makes no sense to talk about a local temperature if things are varying very fast. So clearly, the whole idea of fluid dynamics should be thought of in terms of a derivative expansion. So let's try to not be very ambitious and just try to work out what the form of the stress tensor and other currents can be in the derivative expansion. And the philosophy we're going to take is we're going to write down every term that is consistent with all this invariances and symmetries of the problem and put unknown coefficients behind these terms. Or sometimes known coefficients if we can interpret them. Okay, so let's see how that philosophy goes at lowest order in the derivative expansion. At lowest order in the derivative expansion, so let me try to be simple. Well, okay, at lowest order in the derivative expansion, let's try, for instance, to say what we can say about t mu nu. So what's the lowest order in the derivative expansion? Lowest order in the derivative expansion is 0th order in the derivative expansion. So t mu nu has got to be some function of u mu's, of temperatures and nu i's, and of the metric. Now, what forms have the right index structure? Well, you could have u mu u nu, or you could have d mu nu, but there's nothing else. Okay, it's more convenient for my purposes to use as a basis in the space of these tensors the quantity p mu nu, which I'll define here. P mu nu is equal to u mu u nu plus g mu nu. So p mu nu times some Lorentz invariant scalar plus u mu u nu times some other Lorentz invariant scalar.
Are we still talking about field theory on S3?
No, well, let me to start with be talking about field theory on R4. Okay, it's true that when we're talking about a general curved manifold, you get other possible forms from curvature invariance. I'll turn to that in a moment. But let's start with talking about field theory in R4.
So the metric you have there is just the flat.
Just the flat metric. Okay. You'll see that this result, for my purposes, will generalize to any space very soon. So it will be the metric of the space very soon, but not yet. Okay. Now, what we have the coefficients p mu nu and u mu u nu are Lorentz invariant scalars. Can we interpret these Lorentz invariant scalars? Well, what is p mu nu? P mu nu, you see, is just the projector onto space in the frame in which, once you get into the frame in which the fluids are at rest. Because in the frame in which the fluids are at rest, u mu is 1, 0, 0, 0, Okay, so u mu u nu is 1 with everything else 0, and that cancels the -1 from the metric. Is this clear? Whereas u mu u nu itself is the projector onto time in that same frame. Okay? So now, if we're in the frame in which the fluid's at rest, the part that is the G0, the T00 part of the stress tensor has a name. It's called the energy density, the rest frame energy density. It's often denoted by the symbol rho. Whereas the spatial part of the stress tensor also has a name. It's called the pressure. Okay? So the zero derivative approximation to the stress tensor, or the perfect fluid stress tensor, is determined just by general principles and interpretation to be the pressure times P mu nu plus rho times u mu u nu. Okay, now you remember that I said I wanted to write everything in terms of the variables T and nu I. So you may be wondering what's all this pressure and energy density doing, right? But now this is the next point. Locally, point by point, we'll allow ourselves to use thermodynamics. And thermodynamics determines the energy density and the pressure in terms of chemical potentials. So you can think of both P and rho as being some functions of nu I and T that you know once you know the thermodynamics of the system. Is this clear? Okay, by the way, all we need is this. If we know T and if we know this function h nu I, we know everything that is needed to that goes into this stress tensor. Is this clear? Any questions or comments about this?
What is global constraints if you're on the SC, like there's a global conservation of charges?
You see, the conservation of charges is built into these equations.
Globally, this follows from
From these equations. Okay, good. Other questions? Okay, so now since the whole idea of fluid dynamics is dynamics and derivative expansion, you might think, well, since we've got the only possible form for T mu nu, and by the way, we can do the same thing for J mu I. The charge current is simply u mu times Ri, where Ri is the local charge density of quantity, which can again be determined in terms of temperatures and nu I's. Okay? So now you might think that, well, we've got our lowest order expansion terms, we're through, we should be able to do physics with this. That's almost right, but not quite. That's not quite right because this lowest order approximation to fluid dynamics misses an important physical effect. Okay? In order to capture that important physical effect, we're forced to go to the next order, and that important physical effect is dissipation. In order to see this, you can take the perfect fluid entropy density, which is just the entropy density in the rest frame times u mu, okay, and compute d mu of j mu s. It is a relatively simple exercise using thermodynamics to show, and all these relations, to show that this thing with these specifications is just 0. Okay? This is an exercise I'm not going to go through, but it's a relatively simple one, and I encourage you to try it. Okay, so what do we conclude? You see, this equation tells us that the entropy current is conserved locally. Now, in physical systems, we know that entropy is not conserved, but is produced by dissipation. So this perfect fluid approximation to dynamics misses some things. It misses dissipation. In order to capture the effects of dissipation, we need to go to one higher order in the derivative expansion. Okay, so now this exercise of enumerating all possible forms at one higher order in the derivative expansion and putting coefficients behind the independent forms is more complicated once we include one derivative terms, but can be carried out in the same spirit as the one we've used. There's one extra complication, that is we have to, two sets of equations that are equivalent up to field redefinitions are the same set of equations. So you can simplify your life by making use of field redefinition ambiguity. Okay? Having done all of that, okay, it is possible to show that you can turn the equations of fluid dynamics into these relatively complicated looking expressions. I'm going to guide you through the parts of these expressions for a minute. But none of this will be relevant to what I'm going to say, so don't get hung up on these complicated looking expressions. Okay, well, you see, in addition to the perfect fluid stress part of the contribution to the stress tensor, there's a dissipative piece in the stress tensor. The dissipative part in the stress tensor in general has three contributions. One from what's called bulk viscosity, which is proportional to the divergence of the velocity, this theta bismos. The second was from what's called shear viscosity, which is proportional to a particular form, which tells you about how much the fluid velocities are shearing. And the third from heat flow, where Q mu is the diffusive flow of heat given by a relativistic generalization of Fick's law. Okay, so this is the correction to the stress tensor. Similarly, there are corrections to the charge currents and the entropy current. Okay, the only place I'm going to use any of this, the only way in which I'm going to use any of this is in order to quote for you a result that you can derive if you use these expressions and do the equivalent of this exercise. This is a harder exercise to do, but once again, it's relatively straightforward to do once you get down to doing it. And that exercise, once you complete it, tells you that if you now compute the divergence of the entropy current, instead of getting 0, you get something interesting on the right-hand side. The interesting thing you get is the square of the heat flux plus squares of diffusion currents plus squares of the stress tensor and plus squares of this del dot theta, the bulk tensor piece. Okay, together with certain coefficients, which on physical grounds are forced to be positive. Okay, now I've told you all of this just so that we can appreciate one fact, and that fact is this: if we are, for some reason or the other, interested in fluid dynamical flows that are in equilibrium, or more precisely that are stationary, that are not evolving in time, then this equation, then in particular the entropy density, that is not evolving in either space or time, just have reached their equilibrium, then in particular the entropy current is not changing, so the divergence of the entropy current is 0, okay, and so that ensures that each of these four terms on the right hand side is individually 0. Since we've got a sum of perfect squares, the only way for this expression to be 0 is for each term to be individually 0. So flows in which no entropy is being produced, del mu j mu is 0, are very tightly constrained. Such flows are called dissipation-free flows, dissipationless flows, and they're very tightly constrained. They're much easier to solve for than solving for all of the Navier-Stokes equations, because you're solving much easier equations. Okay, so what I'm going to do now is to solve for at least a large class. I believe this is an exhaustive class, but we don't have a mathematical proof of this, of the dissipation-less flows of a conformal fluid on a sphere. Okay, this will turn out to be a very interesting exercise. Yes?
Sorry for foolish question, but I guess the squares are all Lorentzian squares, right?
Now, you see, everything here has this projection matrix in it. See,
in your expression on the right?
yeah, so because of all these are all spatial, so these are all positive definite.
Thank you.
Okay, so shear is shear spatial velocity.
Yes.
Right. Okay, but it's a good question. Okay, great. Other questions, comments? Okay, good. So what we're going to now do is to solve for at least a large class, and my belief is the exhaustive set of dissipation-free flows on spheres. Okay, so how do we do that? Let's start. Okay, there are several things. Before actually proceeding to that, there's something else I should say. Well, there are two things I should say. One of these came up in David Mateos' talk, or Professor Mateos' talk. Okay, and that went as follows. So far, we've been talking about general fluids, okay? But I will actually be interested only in conformal fluids, okay? So conformal fluids have stress tensors that are more tightly constrained than the stress tensors from our arbitrary theory, because the stress tensor has to transform properly under conformal transformations. Okay? A necessary condition for this is the stress tensor be traceless. And that immediately tells you that this term is absent. So that term is absent in the fluid dynamic expansion for conformal fluids. Okay? So similarly, we don't have this term here in the del mu J mu condition. Okay. So that's the first thing I wanted to say. The second thing I wanted to say was a little bit about the validity criterion for fluid dynamics. Okay, fluid dynamics, remember, is an expansion in derivatives. Okay, how small do the derivatives, or how large does the length scale of variation have to be in order that we can trust fluid dynamics? Well, one way of doing this estimate is by using the fact. One way of doing this estimate is by using the fact that we've already written down both the 0th order and the 1st order terms in our expansion. Now we're doing a derivative expansion. It's unreasonable to expect this expansion to be good unless the 1st order terms are much smaller than the 0th order terms. When does that happen? Okay, so the 0th order terms, the ratio of 1st order terms by 0th order can be crudely estimated as coefficient of this viscosity, this eta, divided by the energy density of the fluid. You see, the 0th order terms are like rho times u. U is order 1. For instance, u0 is order 1. Okay? And and the length scale, of course. Length scale of variation. The first order terms are eta times derivatives on u. U is order 1, but the derivatives are order 1 over r, where r is the length scale of variation. So a crude estimate of the first order by the 0th order terms is given by eta divided by rho times r. Okay, so let's make a definition here. Let's call LMFP eta divided by rho. This is our definition. Notice that this LMFP is a function of temperature and chemical potentials, because each of eta and rho is a function of temperature and chemical potentials. Okay, so the fluid dynamic expansion is an expansion in LMFP, which is a function of T, for instance, divided by R. Okay, so LMFP should be thought of as sort of like alpha prime in string theory. Every time you get a derivative, you get something behind it, and at least a crude estimate of what that thing you get behind it is this LMFP. At least that's the right estimate when you compare first order to 0th order. Now, in order to make this sound more plausible, I want to tell you about a little calculation you can do in kinetic theory. This will not be directly relevant to the calculations we will apply this theory for, because we'll be working strongly coupled n equals 4 Yang-Mills, which is not at all well approximated by kinetic theory, but still gives you physical intuition. Okay, the calculation I wanted to tell you about was that if you try to compute the viscosity divided by energy density in a dilute gas, well, in a gas of molecules that was interacting by kinetic theory, you get an interesting number for this ratio. You find that eta divided by rho is LMFP, where LMFP is the mean free path of the colliding molecules. So this gives you intuition. You see, LMFP is the length scale associated with equilibration. As long as all your quantities vary on distances that are large compared to this length scale, it makes sense to assign local temperatures and local chemical potentials to the fluid. On the other hand, when things start varying on distances that are of order this scale, this whole idea is nonsensical, and the fluid mechanical expansion should break down. Okay? So you can think of fluid mechanics, at least intuitively, as an expansion in the length scale of equilibration divided by the length scale of variation of all your quantities. Provided this ratio goes to 0, the fluid dynamic approximation should be a good one. Okay, so that's all I wanted to say about fluid dynamics in general. Any questions or comments before we proceed to use it?
And you also need to ensure that all the diffusion constants are small, not just eta.
Yes, yes. You need to do this with all quantities that appear on the right-hand side. In the case of the n equals 4 theory, they're all of the same order. So this you should say this more clearly. Yes.
Are you going to estimate how LMFP depends on the Toft coupling in the n equals 4 case?
Yes. You see, if you take this as a good estimate for LMFP, it's already been done for us in the last lecture, because eta is equal to some number times entropy density for strongly coupled Yang-less. This is the classic result of Polycastro starry nets and so on. Okay, so for instance, if we look at the simplest case where the fluid is uncharged, this is now simply the ratio of entropy density by energy density, which is of order 1 over the temperature. It gets more complicated when you start adding charges, but in every case, in a wide variety of cases, we've made this estimate in our paper, which you could just look up.
So then you're going to require that the sphere is much larger than that length scale, right? So that you have some regime. Exactly.
So that temperatures are larger in units of the radius of the sphere. If I take that to be 1, temperatures are large in units of 1. Once we turn on chemical potentials, this will be modified a little bit, but at least in the uncharged case, that would be right. Good. Other questions, comments?
What do you mean by shear viscosity of the sphere? Do you mean locally you think?
You see, shear viscosity is a fluid property.
So the sphere doesn't have translation invariance.
Exactly, but it doesn't matter. You see, it's defined by the quantum field theory. Then you can take that quantum field theory and study it anyway. So it's a property you can compute by looking at the field theory in R4. But then you can look at the fluid flowing anywhere you want. So it's an intrinsic property of the substance. How you compute it is up to you. But once you've computed it, it's there. It's a local property of fluids.
It doesn't depend on where the substance lives?
Well, no. You see, perhaps you're asking, does the fluid dynamic expansion, okay, this is related to another question. The other question is, suppose you're on an arbitrary curved manifold. In the fluid dynamic expansion, you can also have terms for the stress tensor proportional to curvatures, for instance. Okay? You see, this general analysis that we've done so far that's the only place we've used that we're in flat space is by ignoring terms proportional to curvatures. Okay, now if you are interested, as we will be, in flows where the variation of fluid parameters is on the same scale as the as the curvature of the manifold. Okay, so then you can equate manifold derivatives and fluid derivatives, giving them the same weight. All curvatures are second order derivatives. So to first order in the derivative expansion, all such terms are ignorable. Okay? So this expansion is completely correct. It's generally covariant, and there's nothing else you can add that has lower than that one derivative or lower. Okay? So you go to a little Lorentz frame and tells you what the viscosity is. Is this clear? Yeah, you don't look happy, but we'll take it as a yes. Okay. Any other questions or comments? Please.
Are we assuming that R is much different length scale than LMFP?
Yes, that's the regime in which fluid dynamics will apply. Okay? Very good. So this is all I want to say about fluid dynamics in general. Now I want to proceed to use it. So any questions or comments about the general structures is really good time.
So all of this will be essentially in the high temperature approximation.
In the high entropy by energy density approximation, that will all overlap in some regimes with zero temperature, as I will explain to you. Okay, so high something. If there is no charge, high temperature. Okay, good. Other questions or comments? Please.
When we had the equations for fluid motion, one of them was del mu j equal to 0.
Yes, Ji.
And then we looked at del mu j mu.
Oh, I'm sorry. These are two different J's. Oh. There was the entropy current and the charge current.
Okay.
The charge current is always conserved. Del mu j mu I is always equal to 0. That follows from symmetry. But del mu j mu s, the entropy current, is not always conserved. In general, where this dissipation is not conserved. So that's the quantity we looked at.
Okay, thanks.
Sorry about the confusion. Other questions, comments? Okay, good. So now let's proceed to apply this. You see, we're interested, as I've said repeatedly, in the flow of conformal fluids and spheres. So suppose we've got some Sn, and we've got a conformal fluid. I want to find the dissipation-free flows of this fluid. How do I do that? Well, the first thing I want to do is to find the velocity. The velocity is constrained by the fact that the shear tensor must simply vanish, as we've explained. Okay, how do we do that? Well, there is one very general way to. Okay, we can do it in generality, but actually, just for presentation, it's nice to be in one specific dimension. So I'll work in the case of an S3. Okay, how do we make the shear tensor vanish? Well, there's one very general way to make that happen. Okay, and that is to choose u. Okay, so let me choose coordinates on the S3. So let me say that ds squared is equal to d theta squared plus cos squared theta d phi 1 squared plus sine squared theta d phi 2 squared. Where you see what I've done, I've taken S3 and embedded it in R4. Phi 1 and phi 2 are rotations in the two orthogonal planes, and theta labels where you are in an orthogonal direction. Okay, so one very general way to, one set of flows that is dissipation free are those such that u mu, and when I write u mu, I'll write ut u phi 1 ut u theta u phi 1 u phi 2. If we choose this to be gamma times 1, 0, omega 1, omega 2, where gamma is equal to 1 over square root is the relativistic boost factor. 1 over square root of 1 minus cos squared theta 1 omega 1 squared minus sine squared theta 1 omega 2 squared. What is this velocity field? It describes the velocity field of a fluid that is undergoing rigid rotation on the sphere with angular velocities omega 1 and omega 2. Now, you can ask, is this the most generally shear-free velocity vector field on the sphere? Well, it's clearly not the most general thing because we've got a theory with conformal invariance, the whole SO4, 2 invariance. So we can act with that invariance group on this velocity vector field. And when you complete that process, there's a sort of covariant way of saying of labeling these velocity fields. These velocity fields are simply conformal killing vectors on the sphere normalized to have norm minus 1. Okay, in this particular case, it's just a genuine killing vector. Sum of rotations at time translations normalized appropriately. Okay, but you get all conformal killing vectors this way. We do not have I strongly suspect that at least for time independent flows, this is the full class of dissipation free flows on the sphere, but we don't have a mathematical proof of the statement. This is an important point which we'll come to at the end of this talk because it will be related to no-hair theorems of black hole thermodynamics. Okay, but whether or not it's unique, let us proceed with this class of velocities. Okay, fine. So we've got this class of velocities, and now that we have the velocity field, we also want to find the temperatures and the chemical potentials as a function of where we are on the sphere. How do we find the temperatures? Well, we set the heat current to 0. That completely determines the variation of the temperature on the sphere. Okay, it completely determines the variation of the temperature on the sphere to be local temperature is an integration constant times gamma, where gamma is this quantity. I won't go through the relatively trivial algebra that determines this for you. Similarly, we want to find gamma I on the sphere, the chemical potentials as you move around the sphere. That is determined by demanding that Qi vanish. Okay, it's determined to be simply a constant on the sphere. Okay, and this completely fixes our field. So we've got our u mu, we've got temperature, we've got nu I. There's nothing left to determine. Now you can take these fields, plug them back in the Navier-Stokes equations, and check that these are obeyed. It was more or less obvious that it had to be, but you can check that anyway, and they are. So we've got a fine set of solutions, okay, to the Navier-Stokes equations on the sphere. These are dissipation-free solutions. They're very simple and very universal, as will become clearer in a minute. Okay, so these are exact solutions of the equations of fluid dynamics up to the one derivative term. Okay, let's remember how many parameters go into these solutions. Well, let's see. We have the integration constant for the temperature. That's 1. We have the integration constants for the 3 R charges, so that adds up to 4. And we've got 2 angular velocities, so that's 6. So the number of parameters in the solution is the same as the number of conserved charges in the system. That's nice, because there must be at least one dissipation-free flow for every conserved charge of the system. Because if you take a fluid, put it on the sphere, hit it, it has to settle down to something. So every set of conserved charges must settle down to something. So there should be at least one solution per conserved charge. So it should be so it's good that we've got the same number of parameters as conserved charges. Okay, good. Now that we've got these solutions, we can process them. What processing do I want to do? What I want to do is to compute the thermodynamics of these solutions. What do I mean more precisely? What I mean more precisely is to, what I'd like to do is to compute the energy, angular momentum, charges, and entropy of these solutions as a function of integration constants. Now that's a very trivial exercise, because since we know all the solutions, we know all the currents, we just have to integrate them in the sphere. Okay? I am going to give you the answer to this exercise in the form that makes the answer most illuminating. Okay, so what we have is energy, all charges, including the energy, angular momentum, and R charges, as functions of integration constants. We also have the entropy as a function of integration constants. So we have a complete definition of the thermodynamics of the system. Now, we can use this thermodynamics to solve for chemical potentials for this system and solve for the partition function of the system. That partition function, which as a function of chemical potentials would reproduce this thermodynamics. Is this clear? And the answer in this language turns out to be remarkably simple. It turns out to be, firstly, the chemical potentials are very simply expressed in terms of the integration constant. The temperature of the solution is simply K, the coefficient that went behind gamma in the variation of the local temperature as a function of where you are. The chemical potentials, the charge chemical potentials of the solutions are these integration constants. Okay? And the chemical potentials with respect to angular momentum, I've even anticipated by using the same symbols, are also omega, the angular velocities. Some of this, of course, you could have anticipated, but it's sort of nice. Now, so writing the partition function in terms of chemical potentials is the same thing as writing them in terms of these integration constants. Okay? And when you do that, what you get is something quite simple. You find that log of z of beta nu I and omega a is equal to the volume times t cube times h of nu I divided by 1 minus omega 1 squared into 1 minus omega 2 squared. And that's the exact answer. So what we have done then is use fluid dynamics to completely determine the omega dependence of the partition function of any conformal field theory on a sphere in the limit of in the validity regime of fluid dynamics. Okay? The answer turns out to be very simple and very universal, completely independent of all the details of the thermodynamics. You just take the partition function with omega set to 0 and multiply it by an inverse factor of 1 over 1 minus omega 1 squared into 1 over 1 minus omega 2 squared.
What was the reason you were allowed to restrict just to the dispersionless flows and say that gives you, in some sense, the full partition function?
Well, because we're interested in turning on chemical potentials and waiting for equilibrium. Right? It's the same thing you do with, let's say, black holes, with which we'll be comparing. It's the static black holes that define the thermodynamics, the stationary black holes that define the thermodynamics of the system, not evolving geometries.
So these are only kind of
Long time solutions. That's right. Other questions, comments? Okay. I should also tell you what the validity regime of this result is. Well, in order to do that, okay. You see, in order to do that, all I have to do is to take this quantity, this LMFP, and make sure that it is much smaller, than all length scales of variations in my problem. Now, this is a slightly complicated exercise because we have a non-trivial solution on the sphere. So LMFP, which is a function of temperatures and nu i's, varies as we move on the sphere. Derivatives also change on the sphere. So what we have to do is calculate this ratio point by point on the sphere and impose the most stringent condition. Okay? This is also something that takes a little doing, but when you do it, you get a relatively simple answer. You see, LMFP is a function of local temperature and nu i's, but this local temperature, remember, was just gamma times the temperature of the solution. And from conformal invariance, LMFP of gamma times the temperature of the solution is simply LMFP times of temperature times gamma I divided by gamma, because this is the only dimension-full quantity, so it has to depend inversely on it. Okay, using arguments of this sort, and actually using the explicit form of the solution on the sphere, there's a sort of boost factor that cancels this gamma, and the final condition for validity turns out to be that this be much less than 1 on all our solutions. Okay, so LMFP as a function of t and nu I must be much, much less than 1. What is LMFP? Remember what it is. It's simply entropy as a function of t and nu I divided by energy density as a function of t and nu. That is the condition for the validity of what I've said. Is this clear? Please.
So you've set the radius of the sphere to 1?
Yes.
So can I interpret that 1 as saying that you want the mean free path to be much smaller than the space where you are? So
Exactly.
You don't have an infrared cutoff?
Yes. You want one source of variation is the fact that your space is curved. So you want the mean free path to be much smaller than the space we're on. And had this been just for the static solution, things in which nothing was varying, this would have been the rationale for this bound. It's a little more complicated when you actually derive it, because everything is a function of where you are, and there are gamma factors and so on, but they all cancel in the end. So you can use that as intuition to guess this answer.
So actually my intuition was, going back to my question before, that if you want the viscosity to make sense on S3,
yes,
you want the mean free path to be much. So the viscosity is defined in the limit of infinite wavelength.
Viscosity is a fluid property that's defined locally. It's easy to calculate as a pole in R4. But go on, please.
Anyway, my point, if you wanted to use, for example, the Kubo formula, you need to take zero frequency, zero.
The Kubo formula is a tool for computing viscosity.
But it's one way to compute it.
That's correct.
So here you would want, you can't take the limit of zero frequency.
Fine, you could say it that way, but anyway, you could say it that way if you. Yes.
Sorry, I don't think I quite understood. How do you get rid of the dimensions in L mean free path? How do you get rid of them? For me.
How did we get rid of this?
Yeah, sorry, I didn't follow that.
Okay. Let me give you you didn't follow it because I didn't tell you, but let me tell you. Okay. Well, the analysis should be done honestly, but let me give you at least an intuitive explanation. Okay. Suppose you have a fluid molecule. Suppose we're doing this in kinetic theory. Okay. So we had one molecule and another one, such that successive collisions occur at distances of order LMFP in the rest frame of the fluid. Now we should ask, how far do they occur in the lab frame, in the frame in which the sphere is at rest? In order to do that, you have to use the formulas of Lorentz transformation, and that picks up a factor of gamma. Okay? So distances that are small in the rest frame translate to large distances in this other frame, okay? Cancelling this gamma dependence. That's where it comes from intuitively. To say it more honestly, I would have to say much more. That's okay. 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 Good. Other questions or comments? Okay, fine. So now we've got these nice formulas of thermodynamics, which completely determine the omega dependence of the partition function of our theory. But now we should check to see whether this omega dependence is correct. How do we do that? Well, the way to do that is to go back to n equals 4 Yang-Mills theory, to look at black hole solutions which carry all the charges of interest to us, and to compare these thermodynamic formulas with the formulas of black hole thermodynamics. Okay, now the first thing we have to do in this process is to understand what this validity condition translates to in terms of black hole physics. So in order to get intuition for that, let's first set these gamma i's to 0. Okay, so that this is just S divided by rho, and this, as we've said before, is then just 1 over T. So in that situation, the validity condition is simply that we have large temperatures, and that validity condition can be translated into a geometric condition for black hole horizons. And that condition is that the black hole horizon occur at very near the boundary. So in, for instance, the coordinates in which you write ADS space as dz squared plus dxi squared by z squared, okay, you want the horizon of the black hole everywhere locally to occur at zh to be much, much less than 1. See, this you know to be true, right? The hotter you make the black hole, the further out its horizon goes. Okay? So nearer to z equals 0, namely the boundary, the horizon goes. Okay? So at least for this case of uncharged black holes, saying that the temperature is very small is equivalent to saying that the position of the horizon is very near z equals 0. It turns out that in every case that we have checked, this interpretation turns out to be correct. Okay? That demanding that this quantity is much, much less than 1 is the same thing as demanding that the horizon locally go near the boundary. Okay? So we should be comparing these results to the formulas of black hole thermodynamics in the limit in which the black holes are such that their horizon at every point, everywhere on the black hole, and these are rotating black holes, remember, so they're not uniform, but everywhere the horizon approaches the boundary in units, well, at z equal z small, in units in which the sphere has radius 1. Okay, so now it is not a difficult exercise. It's not a difficult exercise to pick up all your favorite papers on black hole thermodynamics in ADS 5. Most of them are written by Chong, Liu, and Pope, and take the thermodynamic formulas from these papers, and Gibbons and Harvey Rial and many other people. That was okay, and take the thermodynamic formulas in these papers and expand them in a power series expansion in 1 over z of the horizon. Okay, you have to say that more precisely, but to say it more precisely, I need more specific formulas. I won't bother to do that. Okay, let me just tell you the result. The leading order in that expansion, in every case we have studied, agrees perfectly with this formula. Okay? So let me list the cases we studied. So while I presented this analysis in the context of ADS 5 cross S5 and in the context of n equals 4 Yang-Mills theory, you've seen that the analysis itself was much more general. You could do it for conformal fluids in any sphere, and you could compare it to black holes in any ADS space. So the checks we have made were to compare, basically comparing this formula with every black hole in ADS space that we were able to find worked out. And this includes arbitrary uncharged this is in ADS-D for arbitrary D. It includes large classes of charged black hole solutions in the situations in which they've been found. So that is in gauge supergravity in ADS-4, ADS-7, and ADS-5. So Okay. I say large classes because the most general black hole solution in these theories has not yet been discovered. So with every class that has been found, we've done this comparison. The classes for AdS5 plus S5, for instance, include those black holes with equal charges under H1, H2, and H3, but no other restrictions. Or arbitrary charges under H1, H2, H3, and arbitrary energy, but equal omega 1 equals omega 2. So pretty large and generic classes of these black holes. Okay, and in every case that we've done this comparison to leading order, and I stress leading order because we're going to turn to something more worrying at the first subleading order in a moment. To leading order, we find perfect agreement. Okay, so that's great. Now, what do we find perfect agreement with? We found perfect agreement with the formulas of black hole thermodynamics. Please.
What is this a test of? Is it a test of their algebra, or because what you put in is conformal invariant?
I'll turn to that in the last. So what I put in is conformal invariance plus what the variables of the system are. Okay, plus the fact that we can describe the system in terms of velocity and temperature and so on. How that comes out of gravity, I don't think that's automatic out of gravity, but I think there's a path to understanding why it comes out of gravity. I'll turn to that in the last 5 or 10 minutes, if you can wait 5 minutes. Okay, good. Okay. Good. Now, the other thing you can check, apart from thermodynamics, is something even more interesting and even more detailed. You see, using fluid dynamics, we were able to find the full solution of the theory. So this includes the detailed form of the stress tensor and the charge density current everywhere on the sphere. Now, using the standard dictionary of AdS-CFT, you can take the black hole solutions and read off the stress tensor as a function of where you are on the sphere, and the charge current as a function of where you are on the sphere in those black hole solutions. So that now gives you comparisons of functions versus functions, not just numbers versus numbers. And those functions also agree perfectly to leading order in every case. Okay, so the agreement is not just a coincidence, it certainly has something to it. Fine. Now, the last, okay. The last thing I wanted to say about this before turning to the disagreement and then turning to Nati's question is about extremal black holes. You see, I want to say a little more about the validity of fluid dynamics. When fluid dynamics is valid. So in order to do that, I've written for you here the equation of state of Yang-Mills theory as deduced from the property of static black holes or black brains. Okay, the equation of state of Yang-Mills theory is written by giving the energy, charges, and entropy as a function of the volume, well, it's all extensive, so that's trivial, the temperature, and 3 dummy variables. 3 variables that you think of as being parameters which you eliminate to get entropy as a function of charges. Okay? These dummy variables are called x, y, and z, and they range from 0 to 1. The thing that I want to point out is that there's a very interesting dependence in these formulas. Every time t appears, it appears in the ratio t divided by x plus y plus z minus 1. Okay? So it's possible to take a scaling limit in this theory in which you take t to 0, but this quantity x plus y plus z minus 1 to 0, such that this ratio is kept finite. In that limit, provided, okay, you can picture the space of allowed values of x, y, and z as the part of a cube, a unit cube, that lies outside the plane x plus y plus z equals 1. Zooming in onto that plane defines a sensible extremal limit in which you get sensible thermodynamics. Okay, but when you take that t goes to 0 limit and x plus y plus z minus 1 goes to 0, all quantities remain finite. Okay, if the coefficient between t and x plus y plus z minus 1 is called chi, then the t dependence is just replaced by chi dependence. So in particular, when you compute the ratio of entropy density to energy, and hence the mean free path, that depends only on chi, and that is small provided chi is large. So there is a limit of thermodynamics. There is a limit of parameters in which you can take the temperature to 0, but also do something to the chemical potentials so as to maintain the validity of fluid dynamics. Okay? This gives you an extremal solution of fluid dynamics. Every point, remember that the temperature of the solution is 0. Remember that in fluid dynamics, the local temperature varied like a constant times gamma. So that constant is 0. So locally everywhere the temperature on the sphere is 0, but the charge density varies as you move around the sphere. Okay? You can take these solutions and compare them to large extremal black holes. And once again, agreement is perfect, provided we're in the limit of large chi. Okay? So I wanted to emphasize that the domain of validity of fluid dynamics overlapped with 0 temperature in the appropriate limit. Okay? So you describe extremal black holes well also by these tricks. Okay, great. Now, a word about the disagreement before I turn to your question. The one thing that in this whole story that we have not been able to understand is that when you take one particular class of black holes, you see everything works, I said everything works perfectly to leading order in every case, but remember we've solved the Navier-Stokes equations including one derivative terms. So everything should work correctly to first subleading order in LMFP divided by R. Okay? Now, unless we've messed up in algebra, but we did it several times, there is one class of black holes in which the black hole formulae and the fluid dynamic formulae deviate at first order in this LMFP divided by R. Okay, this class of black holes is black holes in which all R charges, black holes in ADS5 cross S5, in which all R charges and both angular momenta are turned on, and of course energy is turned on. So all 6 charges are non-zero. For every other class of black holes in ADS5 cross S5 with, let's say, 2 of the R charges turned on but 1 0, or all black holes in ADS4 cross S7, ADS7 cross S4, arbitrary rotating uncharged black holes in other dimensions, the agreement persists including up to first subleading order. But for this one class it doesn't. This we don't understand yet, and it may be an important point to clear up. It may be telling us something significant. It could be that there's some mistake somewhere also. Okay, so that's all I wanted to say about what we've done and what works, and now I'm planning to spend the next 10 minutes on what this means, on Nati's question, how could this have failed, for instance, and so on. Yes?
So the solutions you found, given that they are dissipation-less,
yes,
are they also solutions of the 0th order equation?
Yes. Yes. In fact, you see, by the property that they're dissipation-less, the T mu nu dissipation just vanishes on these solutions. Right. Okay? But there are many more solutions of the 0th order equations than this, which are not legitimate solutions, which would evolve into equilibrium. So these are the right. Okay. So now in these 6-7 minutes, let's try to step back and to see what's going on. In fact, let's try to step back and ask why and when and whether we should expect fluid dynamics to give us a good approximation to solutions of gravity. Okay? In order to do this, I'm going to turn to some, just to remind you about certain basic facts about ADS-CFT. Okay, so let's say we're in ADS, well, it doesn't matter what, but let's say we're in ADS5. Okay, and suppose we were in Lorentzian ADS5. Suppose we were in Lorentzian ADS5. We could ask the following question. What boundary data do we expect to specify good solutions of gravity? Okay? So, part of this question can be answered very simply. Remember that near the boundary, okay, for the purpose of this question, let's turn to the analysis of uncharged black holes. So we can do the analysis just in pure Einstein gravity. No gauge fields, no scalars to complicate our lives. Okay? So remember that if you take the metric and you expand, you solve the differential equation for metric perturbations near the boundary, okay, this thing can be expanded in terms of 2 linearly independent solutions. H1 which is an arbitrary function of the coordinates on the boundary and time, mu nu, plus h2 mu nu, which is another arbitrary function of boundary and time, but divided by, oh well, in my coordinates, times z to the power 4. Okay, this piece is the non-normalizable piece, and this piece is the normalizable piece of the deviations of the metric. Okay, if we are interested, as we are, in studying solutions of gravity in ADS space without, in Yang-Mills theory, without operator deformations, really on the 3-sphere, not changing the metric of the sphere, we should set this term to 0, which we do. Okay, so we're left with these metric deformations. Now, of course, you have to be careful, as always, when dealing with ADS CFT, when dealing with gravity, to factor out pure gauge degrees of freedom. Okay, there's a convenient way of doing that by going to what you might call the Graham-Pfefferman gauge. So in that gauge, you demand that the metric is such that the part that depends on z is precisely dz squared by z squared, and there are no cross terms dz dx or dz dt. All such cross terms just vanish. That fixes gauge invariance to the extent needed for what I want to do. So with this choice of gauge, the only metric fluctuations are hij, where ij refer to boundary coordinates. So anything with a z has been gauged to 0. Okay, now this thing here was a solution of Einstein's dynamical equations, the equations that evolved the metric in the z coordinate. We must also impose the Einstein constraint equations, the equations that are EZI and EZZ. Okay, EZZ does something interesting to hij. It forces it to be traceless. EZI does something equally interesting to hij. It forces a conservation equation at it. This comes from EZZ, Einstein's ZZ equation. This comes from EZI, the Einstein EZI equation. Okay, now it's clear from this equation, but also from the general rules of ADS CFT, that there is a field theory interpretation of this hij. It's simply the boundary stress tensor. Expectation value of the boundary, the expectation value in any given classical solution. Okay, so we'll be looking at some classical solution which is defined by this boundary data. That solution would correspond to a state in which the expectation value of the stress tensor is this quantity. Okay, good. So now Graham and Pfefferman, well, it's basically an obvious statement A, but anyway, Graham and Pfefferman have shown that this state, if you take this, an arbitrary hij2 and an arbitrary function of x and t, then you can take the equations of Einstein gravity and integrate it inwards into, if we're not going all the way, if we're only going some finite distance, you can take this and integrate it inwards. Okay, so if you didn't think very much over some finite regime, if you didn't think very much, you would think that the solutions of gravity are parametrized by boundary data hij, which is conserved and traceless. Okay, now this is almost certainly the wrong answer in a physical sense. Okay, if this was the answer, then this would seem very different from the fluid dynamical answer. It would seem very different from the fluid dynamical answer, as we can see by doing some counting. So let's count the number of undetermined functions Let's count the number of undetermined functions in hij. So if the field theory space-time dimension is d, so that's d into d plus 1 divided by 2 minus 1 because of the tracelessness. Okay? So you would think that this was the total amount of data. You had to specify so many functions of space and time subject to d differential equations, energy momentum conservation. Okay, of course there are many more conserved stress tensors that you can write down of this form than there are stress tensors of the form of fluid dynamics. Let's see how that goes. In fluid dynamics, the number of variables, we've been restricting the uncharged case. So the number of variables is a temperature and of a d velocity. This is constrained to square to d to minus 1. So the number of variables is d. Okay? So fluid dynamics is a specification of a traceless stress tensor, which in general has so many components, largely this is much larger than this, in terms of much fewer variables. So it's a very small cut in the slice of possible boundary stress tensors. Okay, good. Now, the size of this cut becomes even more significant once you impose the equations of motion, once you impose conservation. You see, once you impose conservation, this takes a large number of functions and gives you an initial value problem for some of them, leaving others arbitrary. Whereas in this situation, you have as many degrees of freedom as you have equations. So fluid dynamics is a well-posed initial dynamical system. So you see that the stress tensors that you get from fluid dynamics, subject to energy momentum conservation, are specified by specifying initial data and then evolve according to time, according to the equations of motion. Okay? Whereas the arbitrary stress tensors that you get by this Graham-Pfefferman procedure involves specifying functions of all of space and time and has much more data in it. Okay? So if you were just doing gravitational physics, you were just using symmetries and just trying to parameterize solutions of gravity, you would think there was a much larger class of solutions. However, you see, we know that that's being physically wrong. We know that's being physically wrong because of, for instance, the dual interpretation. You shouldn't in a field theory be able to specify what the stress tensor does at all times. That evolves according to equations of motion. You should only be able to specify initial conditions. So something must be going wrong with this arbitrary specification of gravitational data. Now, there's a very clear guess to what that something is. The guess is that if you specify arbitrary data, okay, then this evolution procedure will lead to an unacceptable singularity inside. Okay? All the data that you can specify on the boundary that will lead to non-singular solutions, okay, should be a very small subclass of the stress tensors apparently allowed by gravity, and in fact should be given by the stress tensors of fluid mechanics. So this is a conjecture that one could make, that the allowed singularity-free specifications on the boundary are of the fluid dynamic form. Okay? But it's a conjecture that is either true or not in Einstein gravity. And sounds to me like a very interesting statement about singularity-free solutions of gravity. It's also actually a statement that one could almost certainly establish to be true if it's true. And some of us are working on this at the moment. So that's my first pass at an answer to your question. Okay, I think I'm done, unless there are questions or comments.
We've got time for 1, 2 quick questions.
When you say that there are singularities, that these generic boundary conditions could give rise to singularities, new singularities, or which kind?
Okay. Yes. So that's a very good question. To be safe, I should just say unacceptable singularities, singularities that are not legal in the theory of gravity. But I have a strong suspicion that such singularities are naked singularities. Singularities that are hidden behind a horizon are okay. Let me explain to you why. Suppose we've got a solution in gravity in which there's some singularity, but it's hidden from the boundary by some horizon. Okay? Now, if you set up a correlation function calculation here, nothing can go hit the singularity and bounce back. That's forbidden by causality. So on this solution, all probes that you make, at least in the large N field theory limit, would be non-singular. So the field theory would see the solution, at least in the large N field theory limit, as perfectly non-singular because the singularities that are hidden behind the horizon are just not visible to it. On the other hand, if you had some singularity not hidden by a horizon, then almost certainly you could rig up some sort of correlation function that would go singular in the field theory, and that would probably correspond to an unacceptable field theory solution. So my guess at the answer to your question is that singularities are allowed, as they often are in gravity, but they must be hidden from the boundary by horizons. Yes?
one more. There's another question there.
Instead of comparing solutions to the Navier-Stokes equation on the gauge theory side with black hole solutions on the gravity side, why can't you just derive the Navier-Stokes equation from gravity?
Yeah, it's the same thing. You see, you have to derive the Navier-Stokes equations from gravity subject to some physical requirement. If you impose no requirement, you can't get anything because an arbitrary Hij is fine. So you have to impose a physical requirement. If the requirement is all singularities be hidden behind the horizon, then that should force the stress tensor on the boundary to take the form of fluid dynamics and the fluid dynamic expansion. So force that stress tensor to be expressed in terms of a local temperature, local velocity, and so on. Actually, we think this is true and we think we understand why this happens, but that's not complete yet. Now, Yannick and his student have done significant and very interesting work in this direction.
Okay, let's thank Shiraz again.